Today we're going to look at Unit 7 Oscillations in AP Physics 1 curriculum. We're gonna break down some basics and advanced FRQs. Let's begin. A block of mass M is attached to a vertical ideal spring of spring constant K. The block hangs vertically from a rigid support and comes to rest at an equilibrium position. The block is then pulled downward by a distance A from its equilibrium position and then released from rest at t equals 0. Assume the subsequent motion is simple harmonic motion and air resistance is negligible. Derive all the expressions in terms of m, k, and g as needed. 1. Determine the period t of the block simple harmonic motion. 2. At which positions does the block reach its maximum speed? Derive an expression for this maximum speed, Vmax. 3. At which positions does the block reach its maximum acceleration? Derive an expression for this maximum acceleration, Amax. Part 1 is asking you the period. So first thing we need to do is trying to identify what kind of oscillation this is. In the question it said, the block is then pulled downward by distance A from its equilibrium and then released. So, as you can imagine, the block is moving up or down with the spring. Is it moving left or right? No, which means it's not a pendulum. We cannot use a formula for a pendulum. So the only formula we can use is t is equal to 2 pi square root m over k. In this situation, it's very easy. You already know the k. M is equal to the capitalized M. 2 pi is constant. So it's just simply equal to 2 pi times square root capitalized M over K. Part 2 is asking you the maximum speed of the block. For those of you who just want the conclusion, I can just tell you right now. During the oscillation, as soon as the block reaches its equilibrium position, the block will have its maximum speed. But I'll still tell you the reason behind it. Now, let's take a look at these graphs. The graph on the left will show you a clear comparison of the motion throughout the entire oscillation. First, you stretch a spring, right, to a distance A below its equilibrium. And there's a very important property of the spring you must remember, which is the spring will always try to reach its equilibrium state because that spring. And then after you release your hand, right, it will try to go back to its equilibrium and then go back again until it reaches distance A above its equilibrium position. And then goes back again because spring wants to go back, right? And then due to inertia, it goes down again. And just repeating this process forever. So first, let's consider when the block is at its very bottom. So like this. In this situation, the spring is trying to go back to its equilibrium state, right? So it'll give an upward spring potential force on the object. And this spring force will contribute to the object an upward acceleration. So during this upward acceleration, or during the process, the upward acceleration keep existing, right? Keep existing because the spring force is still there, right? Until it reaches equilibrium state. So now it has been accelerating since it's at its very bottom, right? So now there's no upward spring force anymore. But when you keep going, the spring is now being compressed and it wants to go back to its original state, right? So now the spring force actually exert a downward spring force, no longer upward, a downward force to the entire system or the object. So now it's started to deaccelerating until it reaches its toppest point or the highest point. And then it's basically the same thing because it's distance a above the equilibrium, and the spring want to go back to its original position, right? Or the original length. It will exert a downward acceleration. So the object will keep accelerating until it reaches its equilibrium, so on, so on. So that's why the object has its maximum speed when it's at equilibrium, because as soon as you goes up or goes down a little bit more, the spring will exert an extra force that is opposed your direction of motion to the object, which will heavily affect your acceleration or your speed. So now, after you know the reason behind it, let's solve it. Obviously, the position is when it's at its equilibrium state or equilibrium position. And at its equilibrium state, right? Originally, it's at rest. So, the net force of the object would simply be Fs minus mg equals 0. And Fs, as we all know, is equal to kx. So, we can solve x. Now, after we know the reason behind the oscillation and the reason behind why the object will reach its maximum speed when it's at its equilibrium position, let's try to solve it. So, at the very bottom, right, when a spring has been stretched for that long, the spring will have a spring potential energy of 1/2 k times a squared. We can actually ignore the original delta x over here, because if you're trying to use it, if you're trying to consider this delta x inside of the problem, you'll do a hell amount of extra work. And it is equal to, at its equilibrium state, right? We can consider this surface, it's the zero potential energy surface. At this surface, it has its maximum speed, no potential energy, which is 1/2 mv squared, which we can solve v is equal to x, no, a, times square root k over m. Part 3 is asking you when will the block reach its maximum acceleration. So we already knew that the maximum acceleration will be achieved when the spring potential force or the spring force is at its maximum magnitude. So we can just write for part 3, A max exists at the highest and the lowest position of the block. So in that situation, kx, we can just use one of the position, right? I would just use when the object is at its bottom position. The spring potential force is going up, right? Then that force will be kx, no, fs minus mg, and is equal to kx minus mg is equal to ma max. And we can easily get our expression for a max, which will be k times the amount of distance that the spring has been stretched or compressed, which will be A over M minus G. And that is equal to your A max. An inextensible string of length L has one end fixed to a ceiling and the other end attached to a small ball of negligible dimensions. The simple pendulum undergoes simple harmonic motion with an angular displacement of theta. For all derived expressions, express results in terms of fundamental dimensions, L, theta, and physical constants are required. Part A. 1. Draw a free body diagram for the ball when it's at its maximum angular displacement, which means when the ball is at its highest position. 2. Derive an expression for the period of the simple pendulum. 3. Derive an expression for the instantaneous speed of the ball when it is at the lowest point of its swing. Part B. Suppose you wish to double the period of the pendulum while keeping the length of the string unchanged. Determine the height above the Earth's surface required to achieve it. Express your answer in terms of the Earth's radius, RE, and the gravitational acceleration at the Earth's surface, G. So part A, or part 1, is ask you to draw a free body diagram. That's pretty easy. So let's first draw a dot that represents the center of mass of the object. At its highest point, obviously, mg, that is pointing straight down, Fg. And the tension force, which is at the same line of the rope. It's supposed to be look like this. And that's it. That's your free body diagram. So for part 2, it's asking you the expression for the pendulum. So first, obviously, we need to identify which formula to use. There's no spring inside of it, so we cannot use the formula that T is equal to 2 pi m over k, right? So the only formula that we can use is T is equal to 2 pi square root L over G. We didn't know the L. That's already been given. We know the G because we're on the Earth. So that's your answer. So for part 3 is asking you the instantaneous speed of the ball. So first, we need to find a way that makes the question easier for us to solve. You're trying to find speed, right? The first thing that come up to my mind is kinematics. However, kinematics are not available over here because the force is changing, so you cannot use it. For the energy, the conservation of energy. Yeah, we can try that. So, at its highest point, it is mgh, right? And it is not moving because it is like going like this, going up and stopped right there, and then going down, speeding up. So at the bottom, let's assume the ground level or the zero potential energy level is the lowest point of the pendulum. And this is equal to 1/2 mv squared. The first thing we can do is cancel out m, obviously. However, we don't know h. So now let's do a simple geometry. Okay. This is the situation that is occurring in this question. We know the length of the string will not change when it's swinging, right? This angle is theta. And we assume this is a ground level. So now we're trying to find this part. How high is this part? So now let's just draw a perpendicular line to the vertical and use a little bit of trick. We can get this is L. We can get this part. It's just L times cosine theta. So this part will simply be L times 1 minus cosine theta. So that's your h. Let's plug it in to the expression. G times L times 1 minus cosine theta is equal to 1 half v squared. Simple algebra, picking the positive solution, v is equal to square root of 2gl times 1 minus cosine theta. Now let's look at part B. Part B is very interesting because it wants you to double the period without increasing the length of the string. So the key way, or the most important way to solve this question is to write a formula down and trying to change or do adjustments to one or several variables in order to reach your goal. In this question, your goal is to double the period. So let's write a formula down. T is equal to 2 pi square root L over G. We're not able to make adjustment to L. Pi is a constant I found 100 years ago. So the only thing that we can do adjustments on is G. So now, let's use one's method. T, right now, let's assume it's 1, is equal to 1 2 pi, right? It will never change, times L over G. L, we cannot do any adjustment to it, so it's still 1. G, for now it's 1, because it's haven't been changed yet. However, we're trying to double the period. So T now becomes 2, because T becomes 2T, and is equal to 1, because 2 pi will never change, times square root of L. L is still 1 because we cannot change the length of the rope or the string, over something. Let's just write A here. What number should we plug over here in order to make the equation, the left side of the equation, equal to the right side of the equation? The answer is 1 over 4. Because, 1 divided by 1 over 4 is equal to 4, and the square root of 4 will give you a 2, and 2 times 1 will give us 2. So G will now becomes, actually I should write G new, will become 1 over 4G. So now let's go back to, I think, unit 2, the gravitational force and the gravitational constant. For G, we have a formula that is G times m, the mass of the planet, over r squared. So now let's use one's method again. So this is 1, right? Because it doesn't change. G's doesn't change. It's a constant, right? It will not change at all. The mass of the planet will not change, so it's still 1. R squared will not change for now, so it's 1 squared. Now the G becomes a quarter of its original value. So now it becomes 1/4. It's equal to 1. G doesn't change. Over the mass of the planet will not change. Over a constant squared. What should we plug in here? Obviously, the answer is 2. 1 times 1/2 squared is equal to 1/4. So your radius supposed to be 2r, which is 2 times the radius of the Earth from the center of the Earth. However, in the question, it is asking you the height above the Earth's surface. So we're supposed to use the actual distance from the center of mass minus the original distance from the center of mass, which is 2r minus r, which will be r, just distance r above the surface or the radius of the Earth. So it is the distance or the length of the radius of the Earth above the surface. A block of mass m is on a frictionless horizontal surface and attached to a spring of spring constant k. The block undergoes a horizontal simple harmonic motion with an amplitude a. At time t equals 0, the block is at its equilibrium position and it is moving to the right. Assume the right is a positive direction. Derive all expressions in terms of mk, a, and fundamental constant as needed. Part A. 1. Determine the period t of the simple harmonic motion. 2. State the position of the block where its speed is maximum and derive an expression for this maximum speed. 3. State the position of the block where its acceleration is maximum and derive an expression for this maximum acceleration. Part B. The origin axis 0 is defined as the natural length of the spring equilibrium position. 1. Derive the displacement function xt of the block's simple harmonic motion. 2. Calculate the time t when the block is at a distance a divided by 3 for the first time from the origin. 3. At what position x is the kinetic energy of the block at the first time equal to half of its maximum kinetic energy? Alright, so number 1 is asking you for the period. In this situation, we must use the formula that period is equal to 2 pi square root m over k, because it's not a pendulum, obviously. So t is just simply equal to 2 pi times square root of m, the mass of the object, over the spring constant. Do you know all these variables from the question? Yes, we do. We know k, we know m. So that is your answer. Part 2 is ask you the position when the block has its maximum speed. I already explained it in the previous question. So basically it's like when you're right here, the spring will be stretched to the longest length, right? So the spring will provide a force that pulls you back from the maximum length. And from here to here, the spring will always provide a force that pulls you towards the equilibrium position, which means from here to here, you're always accelerating. But as soon as you go a little bit further, the spring will you compress the spring, right? The spring will provide a force that is opposed to the direction of the block's motion. So it will you will start deaccelerating instead of accelerating. So you will have the maximum speed when it's at its equilibrium position. At equilibrium, the speed will simply equal to, using the conservation of energy, 1/2 k times the maximum length of the spring, or the delta x. It will be a over here, and it's equal to 1/2 m v squared. This is just conservation of energy because over here you have the most spring potential energy, but the object is not moving. However, in the middle, the spring hasn't been compressed yet. However, you're moving at the fastest rate. So your V will simply be A times square root K over M. Part 3 is asking you the maximum acceleration of the block. So I already explained it previously. As when the spring has been expanded or compressed the most, the block will have its maximum acceleration. So now let's write a net force equation for the block in a horizontal direction, because obviously the block is not moving up or down, it is moving left or right. Net force, when it's at its maximum or the spring has been extended or expanded the most, the net force will just be Fs, the spring force. There's no friction force on the surface because it's stated in the question. Fs is equal to kx. In this situation, x is equal to a, and that is equal to ma. A will simply equal to k times a over m. So for part 1 of the part B is ask you to derive a displacement function xt. So on your formula sheet, you will actually see two interesting equations which looks like something like this. Xt is equal to a times sine 2 pi ft, and xt is equal to a times cosine 2 pi ft. So for a, this is the amplitude, which also means that the maximum distance that the object is from its equilibrium position. For example, in this question, it's very obvious, it already gives you is equal to a. 2 pi is just a constant. F is the frequency. Frequency is equal to 1 over t. So, we're going to break it down, right? We didn't know a. 2 pi is a constant. T is the variable, or the independent variable. We're trying to find, the only thing we're trying to find is f, and it's equal to 1 over t. Can we find t? Yes, we did. We already found that in the very first part in the question. T is equal to 2 pi times square root m, the mass of the object, over k. Let's plug this into the formula for the frequency, which can give us f is equal to 1 over 2 pi times square root k over m. Now we already find the frequency. But which equation should we plug it in? Okay, now let's look back to the question. At t equals 0, the block is at its equilibrium position. For those of you that are hard to understand it, just plug in t when t is equal to 0. So let's plug in the first one. When t is equal to 0, the first equation is equal to a times sine 0, because 0 times frequency times 2 pi is 0, and it's equal to 0. And over here, we assume that the origin x is 0 is when the spring is at equilibrium, which means the block is at its equilibrium, right? So it's right on the spot where the entire system is at equilibrium. So the displacement of it is just equal to 0. So 1 is correct. But now let's plug into the second equation and see if it's correct. T is equal to 0. 2 is equal to a times cosine 0, which is equal to a, because cosine 0 is equal to 1, right? What this means is when t is equal to 0, the block is at its maximum distance from the equilibrium, which is against the question, which is not correct. So we're supposed to plug f into the first equation. But from this, we can conclude that we can use the sine equation when the block is started from its equilibrium. And we can use the cosine equation when the block is at its extreme position, like when a spring has been compressed the most or has been stretched the most. So let's plug f to the first equation. Xt will simply equal to a times sine 2 pi times 1 over 2 pi, which can be cancelled out. So the only thing that left inside of it is the square root k of m, k over m. So that is the expression for the displacement in a simple harmonic motion in this question. So for part 2, it's ask you the time when the block is at a distance a over 3 from its origin. So this is actually pretty easy because we just figured out the displacement formula or expression for this simple harmonic motion, which is x is equal to a times sine square root k over m t. Well, now you should think, because it says it's at a distance of a over 3. It can be either left or right. Let's look at the question. In the question it says, at t equals 0, it is moving to the right. So for the first time, it means that position, which is a over 3 from the origin, is supposed to be on the right. And we assume the right is a positive direction. So it will simply equal to a over 3 is equal to a times sine square root of k over m times t. A can be cancelled out. So sine k over m times t will be 1/3. So if you know a little bit of trigonometry, you'll solve it very easily, which is k square root k over m times t is equal to arc sine 1/3. And t will be equal to square root m over k times arc sine 1/3. And that is your answer. You can plug in arc sine 1/3 in your calculator, and that's fine. It'll give you some decimals, but they're basically the same thing. So for part 3, it's asking you the position of the object when it has half of its maximum kinetic energy. So first, let's write it down and see what it can give us. 1/2 mass of the object times the velocity at that instant. I can write v1 squared is equal to 1/2 times mass of the object, doesn't change, times Vmax squared. And it says half of it, so we need to time 1/2 at the very back. And we can get V1 is actually equal to Vmax over square root. From previous part, we get Vmax is actually equal to A, the amplitude, times square root of k over m. Now it's being divided by square root of 2, so we only need to add 2 in front of m inside of the square root under k. So that is the expression for v1. We'll leave it there for now. And now let's look back to the question and see what it can give us. It said, at that instant, at position x, the object has the amount of kinetic energy that is equal to half of its maximum kinetic energy. Maximum kinetic energy. That sounds quite similar. So when the object has a maximum kinetic energy, right? It's at its equilibrium state. So the spring has not been compressed yet. It's at its equilibrium state. So it has no potential energy. At that moment, the total energy is equal to US plus KE. US is 0, right? So it's only equal to KE. And because of the conservation of energy, the ET will never change. So at this moment, KE has its maximum value. Oh, so KE max is actually equal to the total amount of mechanical energy. So what the question actually means is, at that position, the object has the amount of kinetic energy that is equal to half of the total amount of energy. And let's write down 1/2 times m times v1 squared. I'll just leave it there. It's equal to 1/2 times, no, it's just equal to 1/2 E total. So it only have 1/2 of the entire energy. Where did the other half come from? It must be come from the spring potential energy. So the other half, which is also equal to 1/2 of the total energy, is equal to 1/2 times k times x squared. Oh, now we can solve for x. And we can plug in v1 to this expression to solve for x. So let's connect these two equations together. 1/2 m times v1 squared is equal to 1/2 times kx squared. Cancel out 1/2 and plug in v1, which we can get x is equal to x will simply equal to positive or negative a over square root 2. Because when you plug in this into the expression, you'll find out m can be canceled out, k can be canceled out, basically everything can be canceled out except for the value, except for those like values that you need for the answer. But is it positive or negative? Let's look back to the question again. It says it's moving to the right, and when t is equal to 0, which means for the first time, it reaches when the kinetic energy of the block is half of the maximum kinetic energy is when the object is x away from the equilibrium position and it's to the right, which is positive. So the answer of it is just positive a over square root 2. Well, let's just jump straight into this question because the question itself is quite long. And if you want to look at it, just pause the video, solve it yourself, or at least have a basic idea on how to solve this FRQ. Part 1. The initial speed of the mass, the combined mass. So first, in the question it said the bullet perfectly inelastic collide with the ball, which means it's a perfectly inelastic collision. There must be some loss of energy. We cannot use the conservation of energy. We must use the conservation of momentum. First, let's write the expression for the conservation of momentum. m1 times v1 is equal to m2 times v2. What's m1? The m1 must be the one that provides the momentum to the entire system after the collision. So it must be the mass of the bullet, which is the lowercase m, times v1, obviously, is the speed of the bullet, times v is equal to, after the collision, the bullet and the ball collide together, which forms a bigger mass, which is capitalized M plus lowercase m, times v2. We're trying to solve for v2, which we can easily reform the equation to be v2 is equal to m times v, lowercase m, obviously, over big M plus small m. That is your initial speed of the combined mass. Part 2 is ask you to calculate the mechanical energy loss during a collision. Obviously, the loss of mechanical energy is equal to the initial amount of mechanical energy the entire system has minus the total mechanical energy it has after the collision. Initially, the bullet is moving forward horizontally. Let's assume that the lowest point of the pendulum is the ground level. So initially, the system only has kinetic energy provided by the bullet. After the collision, both bullet and the ball are moving together with initial speed of something we calculated from the last part, and they're not above the ground level yet. So we can just write delta energy, mechanical energy actually, is equal to K initial minus K final. Because we already proved that there's no other energies. There's no energy other than kinetic energy. Initially, the mechanical energy the entire system has is just simply equal to 1/2 the mass of the bullet, the lowercase m, times v squared, minus 1/2 the combined mass, big M plus small m, multiply it by the initial speed of the combined mass we solved from the last part, which is mv over m plus little m squared. After you simplify the equation, you'll get something like 1/2 mv squared times m over m plus m. And then let's check. M over m plus m is definitely smaller than 1. So this number is definitely smaller than the initial amount of kinetic energy. So this is correct. The third part is ask you to derive the expression for the period of the combined mass. Well, this is probably the easiest part because T obviously is a pendulum, so we must use a formula for the period for a pendulum, which is 2 pi times square root L over G. T is equal to 2 pi times square root of L over G. Do we get L in the question? Yes, we did. L is over here. G is a physical constant because we're on Earth, obviously. 2 pi is a constant. So this is your answer, or this is the period of the combined mass. It's not related to mass at all. First part of part B is ask you what is the maximum angular displacement of the combined mass after the collision. If you don't know what maximum angular displacement is, let's look at a graph. Initially, the block or the ball is hanging like this, right? After the bullet hit it, it began to swing. It keeps swinging until it reaches maximum point, which is over here. And that, the angle formed by this and this, is your angular displacement, which is theta. Now let's try to think, how do we solve for angular displacement? So the angular displacement definitely related to some kind of, the use of trigonometry. But we don't know any length yet except for the length of the string. For now, the length of the string is L. So for this, there are two ways for us to solve for theta. The first way is to draw a perpendicular line like this. But in this situation, we cannot solve any lines over here. And the second way is draw a perpendicular line from the new highest point to the original rope, original string. What can we see from it? Oh, that is, we can actually solve for that. Because of the conservation of energy. So let me ask you this. The ball originally only have the kinetic energy. It swings up to this position over here. It began and it stopped. All of this kinetic energy it has over here has been transformed to the gravitational potential energy. And gravitational potential energy obviously is equal to mgh, and the h is this distance over here. So after we solve for h, since the length of the rope is just L, this part of the rope would just be L minus h. And using trigonometry or arc cosine, we can get the expression for theta. So let's begin. First, we need to solve for h. Initially, it has a kinetic energy of 1/2 times the combined mass of big M plus small m times the new speed after the collision, which is mv, little m times v, over big M plus small m squared. And that's equal to the combined mass, m plus little m, times gravitational field constant times h. We're trying to solve for h. After simplifying it, you can do it on paper. You'll get h is actually equal to nv squared over 2g times m plus m squared. And then we can get L minus h. L minus h is just equal to L minus this piece Let's write it down. mv squared over 2g times big M plus small m squared. So now we already know that L minus h, we can just write theta, which is the angular displacement, is equal to arc cosine this over this, L minus h over L, which is one minus mv squared over 2gl times m plus m squared. And that is the maximum angular displacement. So for the last part of the part B is asking you the ratio of the bullet's mass to the ball's mass. And what part 2 basically means is that theta should not exceed 5 degrees. So let's just plug in the maximum value of the theta, which is 5 degrees, and see what we can get. Let's do a little bit of adjustment on both sides, which we can get 1 minus mv squared minus over 2gl times m plus m squared is equal to cosine 5 degrees. After we subtracting 1 on both sides and multiply 2gl on both sides, which we can get mv squared over 2gl over m plus m squared, because 2gl have been multiplied, have been cancelled out. M plus m squared is equal to 0.746. And then we divide v squared on both sides. After plugging 700 meters per second, we can get m over m squared actually. M plus m squared is equal to 1.522 times 10 to the negative 6. Okay, that is the ratio of m squared over m plus m squared. We're trying to find little m over big M. So now we actually need a little bit of math. As you can see, this equation contains m and big M. So now let's use 1 to divide it on both sides. Oh, it's supposed to be negative 6. So it will become m plus m over m. Since both numerator and denominator are squared, which we can put a square on the outside, is equal to around about 657,030. And m plus m over little m, we can write it as one plus big M over small m. Do you see it? It occurs, but it just inversed. So let's write 1 plus big M over small m squared is equal to 657,030. And let's square root on both sides. Pick the positive value, which we can get m over little m is equal to 809.57. The question is asking you the maximum ratio of the bullet's mass to the ball's mass. So it's actually little m over big M. So we must use 1 divided by big M over small m, which is 1 divided by 809.57, which we can get is around about 1.235 times 10 to the negative 3. This is your final answer. A block of mass m rests on a horizontal frictionless table and it's attached to a relaxed ideal spring, a spring constant k. The second block of mass 2m moves towards the first block and an initial speed v, collides with it, and sticks to it. The collision time is negligible. Derive expressions for the following quantities in terms of m, k, and v only. Part A. Please derive the expression for the speed of the combined blocks immediately after the collision. Part 2. Derive the expression for the maximum compression distance of the spring. Part 3. Derive the period of the subsequent simple harmonic motion of the system. First, let's read the question again, trying to come up with some ideas on how to solve the question. In the question it said the block of mass 2m collides with a mass m and sticks to it, which means this collision is a perfectly inelastic collision. So for this type of collision, the energy or the mechanical energy will never be conserved. So we cannot use the conservation of energy. What else can we use? Do you remember momentum? Yeah. So in this situation, momentum will be conserved because there's no outside forces that applied on the system. So let's try the conservation of momentum. Part 1. First step, we need to write the basic expression for the conservation of momentum. m1 times v1 equals m2 times v2. What is m1? Is it m or 2m? If your answer is 2m, you're correct, because the only object that applies the momentum to the entire system will always be the one that's moving, which is 2m in this situation. You can write m1 is equal to 2m. What is v1? Obviously, I already told you with initial speed v. v1 equals to v. What is m2? After the collision, the block 2m and m collides together, become a bigger object, like that. So the m2 will be the total mass of the two objects. m2 will be m plus 2m, which is 3m. We're trying to find v2. Where do you have three variables? Obviously, we can solve v2. v2 is equal to m1 times v1 over m2. Let's plug the number in, or the variables in. m1 is equal to 2m, v1 is equal to v over m2. m2 is equal to 3m. Which, after canceling out m, we can get v2 is actually equal to 2v over 3, or 2 over 3v. Alright, now part 2. So right now we already know that these two blocks have been collided together. So now these two objects becomes like a big object. So right now, the bigger object, you can like imagine like there's a bigger object that is moving inside and compress the spring, right? So now what can we use? The answer is the conservation of energy. Because right now there's no collision happening, right? There's no external factors that will cause the entire system to lose energy. So let's try the conservation of energy. But be warned that as we all know, the conservation of energy means the energy that the entire system has as its initial state is equal to the amount of mechanical energy it has at its final state. The initial state is after these two blocks collided together, not when these two blocks are separated and block 2m is moving forward with a speed v. Be warned. So let's write the basic expression for the conservation of energy. E1 or EI in initial is equal to E final. Initially, what kind of energy does it have? These two blocks are stick together, right? And it's moving. The spring has not been compressed yet. So there's only kinetic energy. 1/2 the total mass of the two blocks. M plus 2m is 3m times v2 squared. The v2 we solved in the last part, and it's equal to, at its final state, the maximum compression distance of the spring, right? Which means the spring has been compressed to like around about here, and the blocks will be no longer moving. So at that moment, the only mechanical energy that left will be the spring potential energy. So this is equal to 1/2 K, the spring constant, times delta x squared. We already know V2, right? We solved it from last part. K is a constant, 3m, we already know that. So let's solve it. But first, we have to write V2 is equal to 2/3 V, because V is the variables that have been given inside the question. Let's plug it in. 2/3 m. I combine these two together to make it look better. Times v2 squared will be 4/9v squared is equal to 1/2 k delta x squared. Now it's just simple algebra. I don't want to waste time on that. After you simplify it, you'll get delta x is equal to 2v times square root of m over 3k. Part 3 is asking for a period, right? First, we need to identify which formula for us to use. In this situation, there's a spring here. There m here. So it's definitely related to the spring constant k and the mass. So we need to use the formula T is equal to 2 pi times square root of m over k. The m is a total mass of the objects, because after the collision, right, both of the objects are sticking together as a whole and doing the simple harmonic motion. Also, if you wonder why we use this formula, just remember that this formula will usually stick to the spring, and the other formula, T is equal to 2 pi L over G, will usually stick to pendulum. Pendulum is something like this. Something will stick to the wall, to the ceiling, right? And it will swing left, right, left, right, left, something like that. Just remember that's basically like the situation that you will use this formula. Now, let's try to solve some of the variables that we haven't solved in this formula. T equals to 2 pi times square root n over k. We already know k. Pi is a constant. 2 obviously is a constant. So the only thing we haven't known yet is m. But it's still very easy though, because since these two blocks are stick together and do the simple harmonic motion, the mass will simply be the total mass or the combined mass of the two objects, which m will equal to 3m, or the m in the formula will be equal to 3m. So the period will easily be solved which is 2 pi times square root of 3m over k. That's your final answer. Alright, that's it for Unit 7 Oscillations FRQ practice. Hope y'all all got extremely high grades on your test. And if y'all have questions, please just type them in the comment section or just straight up sending emails to me. Feel welcome to ask them. I'm very happy to explain them to you. Good luck.